Hello everyone. In this video I want to introduce a set of equations called the integrated rate laws. These are designed to help us calculate an amount of starter material at any given time. And it's going to be based off of the rate laws that we've seen already in the past. And actually what I want to do first is to do a little bit of a review on those rate expressions and rate laws. We'll call this part A, review. And the first one is rate expression. If you recall, if you're given an equation, chemical equation like this, and you want to give the rate in terms of the change in concentrations, then you'll get this equation. Just have to remember that for the reactants, you want to put a minus sign because their concentration is getting lower in number. And also you want to use the coefficients and you put them as denominators to get those two terms equal to each other. And you could express in terms of either the reactants or the product. You're going to want to use this equation if you're given a table or graph with concentrations and time, and the question asks for what is the rate. That's rate expression. The next set of equations, we'll call them the rate laws. This is section A2. And this is where you have to figure out the order of reaction with respect to each reactant. It's still the same rate, okay? Those two rates are identical, it's just different ways of getting at them. And here we have the rate constant. Remember that when you figure out the order, those are the exponents for each of the reactants. And for the most part, they could be 0, 1, or 2. Or 0th order, 1st order, and 2nd order with respect to the specific reactant. And you will use this equation when typically you're given a data table of the concentrations of your reactants and the initial rate that comes from those concentrations. So the table would be of maybe several different experiments, different trials of the same reaction, just varying the concentrations of your reactants. So that is the review that I wanted to go over real quickly. Again, in this video, we're going to see a set of reactions or equations that complement these equations that you see here. Those are called the integrated rate laws. We'll label this B. This is the new material. If you're watching my videos in order, B, new. And I think it's actually super helpful to be very precise with the language. I call this the rate expression, and you're expressing the rate in terms of the delta concentrations, whereas this form is called the rate law, and in an exam problem, you could be directly asked, write the rate law for this reaction. You would have to figure out M and N, and explicitly K if they ask you for K. What's the numerical value for the rate constant? What am I going to call this? We're going to call this integrated. This is the title of the video, Introduction to Integrated Rate Laws. And why would you use this? You would use these equations if asked to calculate the concentration of a reactant. Oh, before I get too far, we should apply these rate laws, integrated rate laws, to a reaction where you have one reactant going to products, at least for now. And not only do we have one reactant, we're going to explicitly think of this one reactant as 1 mole, okay, coefficient of 1. Anyway, if you're asked to calculate the concentration of A at a certain time, I think this is the first equation where we explicitly have a specific time, not a time interval. So if asked to calculate concentration of A at a certain time, given, what do we need? Or solved for, you're going to need time, okay, obviously. Maybe 20 seconds, 30 seconds, what is the concentration of A? You will need to know or be able to calculate the initial concentration, so that's at time 0, and also we'll need the rate constant, or you'll need to solve for the rate constant to do these calculations. Okay, now it actually depends whether the reaction is 0 order, 1st order, or 2nd order. We're going to have 3 integrated rate laws. Let's do 0 order first, 0th order first. And I'm going to put here 4 0th order reactions, or just simply kinetics. Okay. Let me just remind ourselves that this is for a reaction where we have one starting material with a coefficient of 1 going to products. And what do we know about the 0th order kinetics? Well, the rate expression is negative delta concentration of A over delta T. That's the rate expression. That was review. And then the rate law is rate equals K times the concentration of A raised to the 0th power, but anything raised to the 0th power is equal to 1, so rate equals K. The integrated rate laws combine or set these two equal to each other, and we do a little bit of calculus. So let's combine these. And we're going to combine them. I'll write this in purple. Negative delta concentration of A over delta T equals K. And we're going to integrate over values from time 0 to time t. And how does that look like? So I do not force or expect my students to do this calculus. I'm just showing this to show that it can be derived using calculus, these integrated rate laws. Okay. Don't worry if you're unsure of what's happening here. The equation that I need my students to know how to use, I'll put in a green box. But this is the derivation of the integrated rate law. We're going to integrate from initial concentration to the final, and from time 0 to time t. And what this simplifies to, when you evaluate the integral, is this. Let me put it here, next door. So we evaluate it, and we get concentration of A, and that's at some time t, minus the concentration of A at time 0 equals negative kt. And then when we rearrange, that's the time where I want my students to understand the equation. You have the concentration of A at time t equals negative kt, and we bring this over to the right side, plus concentration of A at time 0. This is the first integrated rate law that we should understand how to use. And again, this is for 0th order kinetics, and it's in the form of the line. Y equals mx plus b. Now the thing is, when you plot data for a reaction, this is not always going to be a straight line. It's an equation of a line, but when you start plugging numbers, maybe that line is curved. If the line is curved, then that reaction is not following 0th order kinetics. So what I would write here is, if a graph of the concentration of A versus T gives a straight line, then your reaction follows 0th order kinetics. Then reaction follows, or you can say it's 0th order in respect to the concentration of A, or reaction follows 0th order kinetics if this is a straight line. If it's not a straight line, guess what? We're going to have to double check if this is first order with respect to A or second order. And those are the 3 orders that we're interested in. And we're going to use the integrated rate laws to figure out. Alright, so there's the strategy. I'll get to interpretation of the slope, the y-intercept, after we've seen all 3 integrated rate laws. We're just going to follow the same pattern now. Next is for first order kinetics. First order kinetics, again, rate equals negative concentration of A over delta T. And then for first order kinetics, the rate law equals K times the concentration of A to the first, or just simply leave it blank. Set those equal to each other. If we set those equal to each other, we have this equation. Okay, so it's a little bit different because now we have the concentration of A on the right. You know, in our 0th order kinetics, we didn't. So next is taking the integral. Honestly, I'm not sure how to do the calculus myself, but what you're doing is you're taking the integral again from the concentration of A at time 0 to the concentration of A at some time t, and it simplifies this equation, simplifies to this. Now we have an A on the denominator, which we didn't have, before in the first order kinetics, and oh boy, what's next? Equals. We have t equals 0 to t equals t dt. And then that simplifies or evaluates to what? That evaluates to actually ln of A at time t minus ln of A original concentration equals, again, negative kt as before. Good. And when we rearrange, just like we did up here for the 0th order kinetics, when we rearrange, we get now this integrated rate law. ln of A at time t equals negative, again, kt plus ln of the concentration of A at the beginning at time 0. This is your second integrated rate law. And when is this a straight line? It's a straight line when A, or the reaction, is following first order kinetics. If it's not following first order kinetics, this would not become a straight line. It's an equation of a straight line, but it wouldn't fit. The data actually wouldn't fit to a straight line. So again, if reaction follows first order kinetics, then not this will give a straight line, but that will give a straight line. And what's going to happen here when you start doing practice problems, you'll have data, and you could probably read off the graph or from the data table what the initial concentration of A is. You'll have to most likely solve for k. That's actually the negative slope. You'll be given a time, and you're expected to calculate the concentration at that time. More on that in just a bit. We have one more for second order kinetics. This is B3. For second order kinetics. You won't be expected to derive any equation, any integrated rate law for anything besides zeroth, first, or second order kinetics. And did I say derive? You won't be expected to know the integrated rate laws for anything besides zeroth, first, and second order kinetics. Same exercise, people. Rate equals negative delta concentration of A over some interval of time. That's the rate expression. The rate law is the concentration of A squared times K. Combine those or set them equal to each other, and again, I'll do this in purple. Concentration of A over delta T equals K, right? A concentration of A squared. Take the integral. I'm going too fast, you're definitely free to pause. So this is where it gets a little bit tricky. Well, for me, math was always tricky, but this is especially tricky. We're going to bring the a squared to the other side, equals 0 to t. Oops, I forgot. This is negative k dt. Now, evaluating this integral, what you actually get is this negative 1 over concentration of A at time t minus, all right, let's see what's happening here, minus a negative 1 over the concentration of A times 0 equals now, no, still negative, negative KT. Okay, so this is going to be a little bit weird. I'm going to switch everything to the other side. So negative KT comes to the left, it becomes positive KT. Actually, this one stays, and then this one goes to the right. You will get, and this is the one in the green box, 1 over AT equals, now positive KT plus 1 over A initially, concentration of A at time 0. The thing is, when you're analyzing your data, concentration of A versus T, and you graph based off of this equation, if it's not a straight line, it is not zeroth order kinetics. Then you would want to graph this equation, where you change all the concentrations of A into the ln of the concentrations of A. Graph that versus time, and if that's a straight line, then the reaction follows first order kinetics. But if even that is not a straight line, then you want to graph 1 over the concentration of A versus time, and then hopefully that is a straight line. So again, if this equation gives a straight line, then your reaction is following second order kinetics. What is the implication of that? The implication of that is then you're allowed to use this equation to get the K. Rate equals K A squared. you get that K. Okay, maybe they give you enough information, they give you the rate. You get that K, you plug it back into here, and if you know the initial concentration, then at any time you could figure out the concentration of A. Okay, I have here a summary. Before I show you the summary, a good exercise would be to take all of these integrated rate laws and ask yourself, what do these equations of lines tell you? Okay, what can you get from them? All right, I'm about to show you a summary from a textbook, but again, you should be able to do this on your own. Reorganize your notes, and is this the same thing that we went over just now? Look at your equations that are circled in pink. Those are the 3 integrated rate laws that we had just written down. What about the slope? Right, I asked you, or I told you that we would discuss slope a little bit. Here the slope, m, equals negative k. So the first two, yes, the slope is going downward. Okay. Not only that, not only can you get the rate constant, which is super important to be able to use this equation, you could also get the initial concentration of A, because that's the y-intercept. So this point right here is concentration of A if the reaction is following first order kinetics. Now, if you're looking at the y-intercepts for the other two, you just got to remember that the axis is not concentration. The axis is now ln of concentration, or 1 over concentration. But you could still, right, you could still solve for the initial concentration of A to get that number there, and then you could figure out the concentration of A at any time. Does that make sense? In previous videos, we had discussed also the units of K, how they need to change so the rate ends up being most likely molarity per second. So here, I don't expect people to memorize this actually. I expect people to be able to figure it out based on the rate law expression. Alright, the next 2 videos, at least 2 videos after this, we are going to use the integrated rate laws to solve for what? To solve for the concentration at a specific time. 0th order integrated rate law, 1st order integrated rate law, and finally we'll see the 2nd order integrated rate law in these practice problems that I'm going to show in the next 2 videos.